Why not use Newton's laws for everything? Why do I care about that? Well, I'm trying to deal with quantum mechanics, and quantum mechanics says don't use Newton's laws. Now, how can that be? Are Newton's laws wrong? No, they're not wrong. They operate just fine. You say that, okay, an object in motion stays in motion. Every force has an opposite and equal reaction. And this force thing that Newton identifies as primarily important to his ideas equals the change in momentum. The change in momentum. Now, why do I say momentum? Well, I'm trying to get away from mass and velocity as separate entities. I'm just trying to use momentum. So, uh, how does that relate to things? Well, let's talk about energies and how that really applies to ways things move, the way things move in motion. And rather than Newton's laws, in this video, I'm going to talk about the principle of least action. Now, that doesn't make any sense to me on the surface. So let's use this time to focus on what principle of least action is all about. Let's take the case of kinetic energy. Kinetic energy, which in Newtonian mechanics or Newtonian world is 1/2 mv squared or p squared over 2m. That uses the momentum value of p and does the same thing as 1/2 mv squared. That's the kinetic energy. The kinetic energy that stays in from Newtonian all the way through all these other ideas that we've come up with. So, kinetic energy is not the total energy. You have to consider the potential energy. And the potential energy has different ways of forming that or different ways of expressing it. And that kind of gets us to this principle of least action. If we focus on kinetic energies, then this will help us see what's going on. Now, before I talk about the principle of least action, I'm going to talk about Fermat's Fermat. This mathematician, what did he say? Well, let's look at his principles in this video and see how that can relate to least action. This is a discussion of light. Now, how did I get from Newton's laws to light to not using Newton's laws? Let's explore this a little bit more and see if we can come up with some results. First of all, light travels in a straight line, right? Always. Light travels in a straight line. That's the least effort to go in any direction. You always follow a straight line. But what happens if light bends through glass? Well, it goes up and it bends through glass, or it is refracted. And what about if light is reflected? It's not going in a straight line anymore after it's reflected. So what happened to that? How do we express that? And that's where we use this principle of Fermat. I think it's Fermat rather than Fermat, because in French, probably the T has a soft sound of Fermat. So anyway, I need to check that out. Anyway, the light, if it doesn't travel in a straight line, then what principle tells us how refraction works? Let's think of it this way. The kinetic energy of light, kinetic energy of light, what could that be? Well, the mass of a photon is 0. So how do we get kinetic energy out of 1/2 mv squared? Well, that's why I'm going to go back and use this value of p squared over 2m. Now, light doesn't have mass, but it does have momentum. So if it has momentum, then that means that when it goes through glass, the velocity of light is less than when it goes through a vacuum or even through air. So that means that the kinetic energy is changing. So if the kinetic energy is changing, the principle of uh, least action says that we want to use the most efficient use of the kinetic energy to get from point A to point B. And in some cases, like when it goes through glass, it when it slows down, then the kinetic energy is less, and we have to come up with a different path than the straight line. How are we as far as following along with this? What I want to try to do is make this similar to why physics, to try to bring in everybody that might click on this and view it. So let's talk about the refraction of light. I'll go to the drawing board. We'll talk about kinetic energy of light and then come up with some ideas from that point. Before we talk about light, I thought I'd choose an example that made this idea a little bit simpler. Let's say we want to get from point A to point B in the least amount of time. Say I'm using Google Maps and this is city A and this is city B. We're trying to figure out how to get there in the least amount of time. Google Maps will say, what's the least distance? Here's 60 miles. Or what's the least amount of time? This is 75 miles. So this path, this green and red path, is according to the principle of least action, the route that will be taken. Just to go over this quickly, 70 miles per hour, 70 miles takes you an hour. Going 5 more miles to get to destination B after we exit from the interstate, that's going to be 0.1 hours at 50 miles per hour. And this other one, 60 miles, is going to be 1.2 hours. So you will arrive 6 minutes earlier if you take this route up here. Of course, you might burn more gas or other things might happen. But if we're optimizing the time, which I don't know how that works out with the kinetic energy part of this, but let's step into this next with the idea of light and how the paths of light are affected by least time. Okay, now on to light. Fermat's principle states that light travels between 2 points along the path that requires the least time. It doesn't say the shortest distance, it says the least time as compared to other nearby paths. So out of all the paths that are chosen, it's going to take the one that takes the least amount of time. So let's start with the law of reflection. I actually think the law of refraction is a little bit easier, relates more to that last thing that we talked about. But let's talk about this law of refraction, see if we can make some sense of it. Okay, let's consider two ideas. One is, what's the shortest distance between A and B? Shortest distance, well, that's pretty easy. We already plotted that earlier. It's a straight line from A to B. Well, that's not a straight line. Let's try it again. Let's try to get it at least somewhat approximating a straight line from A to B. Okay, that's pretty close. That's the shortest distance. What is the quickest route? And that's what we're concentrating on. And that's what the photon is concentrating on. Now, remember, light is made of photons. So let's talk about it this way. Here's the photon, and what does the photon want to do? Well, according to Fermat's principle, and also this principle of least action, which is very important for how we're going to look at things, the photon gets there the quickest. Well, speed of light is really quick, and the photon wants to go the quickest route. So, what's the quickest route? Well, let's look at some stuff here. Which one's faster? The speed of light in air is faster than the speed of light in glass. So let's think of it back to that analogy where we were doing a Google map layout of how to get from one place to the other most quickly. Here I'm spending more time in the fast lane, and here I'm spending less time in the fast lane. So that means if I'm spending less time in the fast lane, that means I'm spending more time in the slow lane. So all this is done to optimize the time. Okay, got that pretty straight. That should come out pretty easy to you. Now for the part that takes a little geometry. Here's how we measure time. In other words, we're trying to prove this with math. Here is the time, and here is the distance over the speed. Distance over speed gives us time. 50 miles over 50 miles per hour will give us how long it takes to get there. In that case, it takes 1 hour. So, how does this represent the distance? The distance is this hypotenuse, which is the square root of this dimension squared and this dimension squared. So that's where the x squared plus h sub 1 squared comes from. The c over n plus n sub 1 is speed of light over the index of refraction. And this index of refraction tells us how much do we lower the speed of light if we're going through air or if we're going through glass over here, n sub 2. Now, one thing that confused me initially was, what is this? It looks like a 1 here. Actually, that's an L. So the L is from the total point, that you think of it this way, the total distance, the total horizontal distance between A and B is L, and the total vertical distance between A and B is H1 H sub 2. So, what about the different horizontal distances? This is x. In other words, that's the variable that we're trying to talk about. The x can change from one place to the other. And this is not 1 minus x. This is L minus x. L for the distance or length here. So, here's the two situations. This covers the distance here and the speed, and this covers the and this one here, this one covers the distance there. 1 L minus x squared plus h sub 2 squared. There's the time. Now, if you know how to take derivatives, this next part will make sense. If you don't know how to take derivatives, well, I'm going to walk you through it. And in order to do that, let me bring up another screen where I kind of expanded it out. We'll come back to this screen after I go through my little scenario, because it's a lot more clear and it uses nice text symbols, whereas I'm going to free draw it here on this other picture. Okay, there's the t. There's the L minus x. So don't let that L confuse you. Here's the derivative. The derivative rule for exponents is that you put the exponent out front. Square root is 1/2, and then you lower or you reduce the exponent by 1. So if you take 1/2 minus 1, you get a minus 1/2. And then we have to take the derivative of this inner part with respect to x. The h squared is a constant, so there's no change with the h squared as far as x is concerned. Again, I take the exponent out front, 2, and lower the exponent by 1. So that leaves me with 2x out here. 1/2 times 2 just leaves me a 1. And so that leaves me x times x squared plus h sub 1 squared. That means the square root's in the denominator. And here's the n1 over c. In a similar manner, I'm going to work with this one, and we'll see that, again, we take the 1/2 out front, and this one has an exponent of minus 1/2. Let me get that fixed here. Let me put a 1/2 out there, or minus 1/2 out in front of this one. Here we go. Let me reduce this so it's nice and narrow. That'd be a minus 1/2 to that exponent. Then here's a little difference here because I've got L minus x. Put the 2 out front. Here's the 2 out front, L minus x. And then I take the derivative of this inner part, and that's going to be L is constant as far as x is concerned. So I take the 1 out front, that gives me a minus 1. X to the 0 is just 1. So here's the result. Now let's go back to that other screen and see if it makes sense to us. Let me find the screen so we can look at it. Okay, here we go. Let me get my cursor out there so we can see what's going on. Here's the n sub 1 minus n sub 2 here, and we set those equal to 0. Why do we set it equal to 0? Well, when the derivative equals 0, that's either a maximum or a minimum point. In this case, that's going to be a minimum point. So if these two are equal to, these two added together are 0, then I can put this minus quantity on the other side of the equals sign, and that'll make it a positive. So here we have it. Here's a positive, n sub 2, and here we go there. Now, where in the heck do we come up with this value, which is actually a very important thing called Snell's law? To understand why this is sine of angle 1 and sine of angle 2, we have to go back to the right triangle definition of sine. Sine is the opposite over hypotenuse. Opposite meaning opposite of angle 1. Angle 1 is shown here, and that angle 1, using the rule of opposite angles, is also the same as this angle right here. So if that's the case, then we look at the opposite side from this angle, that is x. The opposite side from this angle is L minus x. So there's x, L minus x over the hypotenuse, So that gives us the fact that these are the sines of each of those angles. And these are the index of refraction values. Think of it. We just explained why light doesn't travel in a straight line. Light travels in a line that is the quickest path.